How many times did you send a text yesterday? To the right, we see a small frequency distribution of potential texting amounts. We can describe these amounts as a whole in several ways based on measures of central tendency. The mode is the most common value found in a data set for a particular variable and will be the highest region of the distribution, such as when plotted on a histogram. The median is the middle value or mean of two middle values. It does not have to be an actual value. The mean is what we normally refer to as the average. To find the mean, we add up all the observations, divide by the number of observations. The mode and median are mostly unaffected by outliers or extreme scores, but the mean is algebraic and provides a better estimate of the full population. When the distribution is asymmetric or has many outliers, the mean, median, and mode can all be quite different from each other. We might consider a trimmed mean. It is useful to remember that the mode provides the information that we use to determine whether a distribution is unimodal or bimodal. If I were in sales, selling electronics, I would want to know what item or items were selling the most. In this case, the mode would be very important. However, usually it is the most useless and least used measure of central tendency. The median is defined as the middle score in an ordered set of data and is also referred to as the 50th percentile. The book refers to the median location, which is the position in an ordered distribution occupied by the median. It is not extremely important, but can help us find the median by using the number of items in our data set, adding 1, and dividing the sum by 2. The result provides the location of the median. The mean is represented by the symbol X bar, which looks like an X with a line over the top of it. It may also be represented by an M. When the distribution is nearly symmetric, the mean and median will be close to each other. If the distribution is symmetric and unimodal, the mode will also be in general agreement with the mean and median. When the distribution is asymmetric or not normal, all three values of central tendency may differ substantially. Understanding the strengths and weaknesses of each measure of central tendency helps us decide which one to use in different situations. The mode is always a value that actually occurred and represents the largest number of people having the same score. It can also be used with nominal data. One advantage of the median is that it is unaffected by extreme scores. This was also true with the mode. When we want to describe a distribution without deference to the extreme scores, we would be likely to use the median. However, the median is more difficult to use in algebraic formulae. It is also not as consistent or stable from one sample to the next. This presents problems when estimating parameters. The mean is influenced by extreme scores, pulled positively or negatively by outliers. Its value may not exist in the actual data set. However, the mean can be manipulated algebraically. We can write the equation that defines the mean. When we draw a mean from a sample, it is called a sample mean. As we draw more and more sample means, we are better able to estimate the population parameter. Sample mean is stable and consistent, thus making it more reliable. One way to reduce the effect of extreme scores is to use trimmed means. To do so, we could take one or more of the largest and smallest values in the sample and exclude them before calculating the mean. We might consider using a 10% trimmed mean, setting aside the largest 10% of the observations and the lowest 10% of the observations, resulting in a 10% trimmed mean. It is important that we take the same percentage of numbers from the top as from the bottom. While I have not seen these used often, they can be used and useful with skewed data. Look at the data set that we have, or that you have, and find the mean, median, and mode for several variables. What did you find? Pause if you need more time. When we talk about measures of variability, we're trying to understand how groups differ. Generally, we use a measure of central tendency of each group to compare one to the other. Usually we use the mean or average. On this slide, you see graphs that show variability in opinions about net neutrality by age and across political parties. The average may reflect the general location of most scores, or scores could be distributed over a wider range of values, and the average may not be representative of most of the observations. Measures of how representative the average is allow discussion of dispersion or variability around the median or the mode or the mean. Remember that we are not interested in variables that do not change. There is little incentive to study things that everyone agrees on or things that have been proven. The range is a measure of distance between the lowest and highest scores. These may be outliers, or they may be fairly consistent with a symmetric dispersion. However, if they are outliers, the range will be much wider than if these outliers were trimmed. As we've discussed previously, trimming a dataset may allow us to have a more representative range that is less affected by outliers. We could use the interquartile range, which represents a trimmed dataset, cutting off the top 25% and the bottom 25%. However, the interquartile range may not include good data. By using it, we lose 50% of our observations, such that our range may no longer be a good representation of our overall variability. Rather, we might like to focus only on removing errors or extreme outliers. A 10% trimmed sample might be more appropriate even. Speaking about variance, we will look at deviations from the mean. Since we do not use absolute value, we must square the values. Take a look at the white box with yellow arrow pointing to it. We find that the mean is 3.3 repeating, and the sum of the deviations from the mean is 1 minus the mean plus 4, minus the mean plus 5, minus the mean, all divided by 3. Note that the result is 0, giving us no information about how values deviate from the mean. The values always balance each other out if we do not use squaring to obtain what's called the sample variance. The sample variance allows us to square the deviations and add them up rather than simply adding the deviations themselves. In doing so, we avoid negative numbers that cancel out our positive numbers. In fact, we will replace the divisor with n minus 1 because it ends up giving us a better estimate of the population variance. Here we work through a formula. The sample variance is equal to sigma times each x minus x bar squared divided by n minus 1. From the example, we get two sets of data. The mean of the first set is 2.64. As we look at the sample variance, note that we work within the parentheses for each value of x in the mean and square, and we square it before adding deviations together, and we divide by the number of values minus 1. We'll come back to the standard deviation shortly.